So you have seen the prime number theorem already. The first week was devoted to first 4 days were devoted to this topic, prime number theorem. So what's going to happen now is that we are going to have the primes are not going to be all primes, but they're going to be primes which will depend on a modulus condition. So that then now you can guess that the zeta function will be replaced by an L function. And this is a nice, of course, in itself, a very nice area to study, but it's also nice because we have just looked at the zero-free region. Yesterday, we studied the zero-free region, and we studied everything that we have studied till now is going to find an application in the proof of this theorem. And it apparently looks quite simple. It's not all that simple. Yeah, it's not all that simple. And so intuitively, where do you think the difficulty is going to come from? Depending on what we know till now. Where do you expect a difficulty here? What is new? What is new between, so what you're trying to find is the number of primes. Oh, এটা কি কোনো জরুরি কিছু লাগিয়ে নেব where is the difficulty, where do you expect, what is different? I mean, something that we studied yesterday, it's the existence of a possible zero, the Siegel zero. That's what makes getting uniform results difficult in the case of the prime number theorem and arithmetic progression. So it's a nice application of the things that we saw till now. Okay. So yes, so we will use some notations. You know them all. I mean, you don't know them all, but you can guess them all. So you saw that our aim for the prime number theorem, the classical prime, the usual prime number theorem, is to find the number of integers that are less than a certain bound, yeah, to find some results for that. The first thing is, of course, very simple, that there are infinitely many primes that we know. And then, so the similar thing here we have seen, there are infinitely, in the first day, on Monday we saw this, that there are infinitely many primes in arithmetic progression. And now we want a qualitative result to show this. So let us take we will take the notations that we will use are the notations that are parallel to the prime number theorem without arithmetic progression. And so this is pi x q a. Okay, the new thing here is the q. So this is the number of primes which are less than x, but not all primes, but these primes are congruent to a modulo q. All right. The other thing, the smooth version of this is going to be psi x q a, and this is going to be defined as all primes which are less than, so this time we are going to have lambda of n, okay, n less than equal to x and n congruent to a modulo q. All right. Lambda is the von Mongol function. Yeah, you remember this? Lambda of n is equal to log p if n is a power of a p, prime power p, and it's 0 otherwise. So use of this makes life simpler because this is smoother, and then by partial integration, you can get back the pi. Okay, and so we will take, as usual, we will take L of okay, and we'll just I will write that a bit later. L will simply be a Dirichlet function with modulus q. Okay, so the case q is equal to 1 is the Riemann zeta function. All right. So yeah, A and Q should be co-prime. So I want to recall things that you already know. So if A and Q are co-prime, this condition is to make the definitions consistent. So we always have this A and Q to be co-prime. And then we get a, you know how we get a linear combination of characters. So these are just, I'm just writing them out, though we have seen them before. So we get this. If I take the sum of chi bar A and chi of n, take the sum over chi, and I normalize by the Euler-Phi function, then this, you know, you remember this? It is either 1 or 0. So it is 1 if we have n from the congruent class, n is congruent to A, and otherwise. So now, if I multiply this, if you multiply this by lambda of n, okay, the von Mongol function, then, and then we take the sum, what we are going to get is psi x q a in terms of this. So multiplying by lambda n and summing, what we get is, take the sum over chi, same thing, chi bar of A and then we write psi of x chi divided by phi of q, and this is equal to psi x q a. So yeah, you remember what psi is. So the notation is clear now. We can remove it. You remember this, psi? So psi of x chi, this is sum of chi n lambda of n, where n is less than or equal to x. So this is the equivalent of the psi of x that we have for psi of little x that we have for the prime number theorem. Okay. So now we will use, what we will use is an explicit formula for psi x chi. Okay. So we use an explicit formula, and much of our effort will be in obtaining such an explicit formula for psi x chi. Okay. So because if you have psi x chi, then you can use that to get psi x q a. All right, by this result. So the theorem that we propose to prove is an explicit formula, and let me write it out. So first let me write it, and then I will tell you what is. So here is our theorem. It says that psi x chi, this is equal to E0 chi into x. You remember E0 chi, we've used it before. It's either 1 or 0, depending on whether chi is chi 0 or not. And then an error term. And what does this error term look like? This error term is big O of x exponential minus C1 square root of log x. Okay. This is the result when there is no exceptional zero. And when there is an exceptional zero, we get this to be equal to minus x beta 1 by beta 1. The exceptional zero is called beta 1 often, plus the same error. The exceptional zero is the zero we saw yesterday. I mean, we didn't see it. We don't know if it exists. So we said that it might exist. Nobody has seen an exceptional zero yet. So nobody really wants to see it. We don't want an exceptional zero, but we don't know how to get rid of this. Okay? And so what's wait, this is not, you didn't stop me. such a wonderful result cannot exist, right? So this depends on the Q here. If so, Q is less than equal to exponential 2 times C1, the 2 is not particularly exciting, square root of log x. Okay? And E0, so that's the bad one. You see, it's this bounds that are, in such results, it's these things that are not good. And these things that we don't know how to really make very good. Okay? So there's one thing that is not yet, yeah, it is, but which I should say, E0x, E0 chi, this is either 1 or 0, depending on whether chi is equal to chi 0 or not. Okay? Okay. So now we will prove this explicit result. So you remember, and this we did in the last classes, that maybe 2 days ago. So I'll keep the theorem over there, and so if we have an explicit result, explicit formula for psi x chi, from here we can get the prime number theorem, or the form of with psi x q a, from which getting the prime number theorem is a trivial affair. So let us concentrate on this. Okay. So the proof. Do you have any questions? So how does the proof go? So you remember that use this. If I take L prime by L, okay, of S chi, then this is equal to the summation of lambda n pi n by log n and n to the power s for n going from 2 to infinity, and sigma greater than 1. That's not true. No, if I take L prime by n, then there is no, this is if I write simply L prime. So chi n, there's no log here anymore, and I can go all the way down, n to the power s. This you remember. We did this, yeah? And we use this to write psi x chi, okay? Psi x chi, this is equal to, so this is minus 2 pi I, the integral from sigma 0 minus I t, sigma 0 plus I t, L prime by L S chi x bar S by S plus a certain error R for sigma 0, which is greater than 1. This is a standard technique. You remember this. And so what I will try to do is, I will have a rectangle, and as you do in the prime number theorem, which you have seen the proof. Okay, so as in the proof of prime number theorem, what we do is we take t to be at least 2 and to be less than x, and we take the sigma 0 to be equal to 1 greater than 1, remember? So something like a small thing, 1 plus log x. Okay? And this r that I have written here, this r is bounded by x by t log square of x. Okay? So as in the prime number theorem, we take a closed contour which contains of 4 points. You know which 4 points it's going to take? We're going to get a rectangle, and this, and then which 4 points are you going to take as in the prime number theorem? So you already can see 2 of them, sigma 0 plus it, sigma 0 minus it, and then I need 2 more, which I will choose. I'll take something. So the choosing, of course, I will choose, but the choice is not something easy. Why? Why is the choice not easy? Can you somehow? I want to contour. What should I expect within this contour? I'm going to take an integral here. Okay. So what should happen? What should happen in this is that the exceptional 0. So I have to be able to manipulate my exceptional 0. Okay, I have to choose the points in such a way that I still have some control over that. Okay, so use a closed contour. Let me call it C. Okay, which joins these 2 points, these 4 points. So it's over there sigma 0 minus it. So there is a t. There is a t up here somewhere, t minus t here, sigma 0 and minus sigma 0. Yeah. So so sigma 0 minus it, sigma 0 plus it, and then I will have 2 more points, sigma 1 plus it and sigma 1 minus it. Okay. So what do we have to do? The importance is to choose the sigma 1. So it is important to choose sigma 1. this sigma 1. Yeah, we choose sigma 1, and what should sigma 1 do? Sigma 1 such that the contour does not pass close to 0. Close to the exceptional 0. So by close, when I say close, I can use the results that I know, the results that we have talked about yesterday, that where can the exceptional 0 not be? All right, where can it not be? So now we are going to do a case-by-case work on this theorem. Okay, so theorem. So that's you remember our theorem. And so first case is the easy case. So what is the easy case according to you? What is the easy case? Tell me. This time you're going to break depending on the 0, not on the chi. So which is the easy case? Where can it work like the prime number, classical prime number theorem? When there is no exceptional 0. Yeah? When there is no exceptional 0, we are in the old case of the similar case as. So we'll do that first. All right. So case 1. So there'll be 3 cases. So case 1, when there is no exceptional 0. Case 2, when there is exceptional 0. So what is case 3? Case 3 is case 2 broken up into 2 parts, when the exceptional 0 will be close and when the exceptional 0 will be firm. Okay, these are the 3 cases that we will look at. So that's when I promised you that we are going to use exceptional 0, I'm keeping up my promise that we are going to use them. Yeah. So it was not just for fun that we introduced them. I mean, maybe someday exceptional zeros will be just for fun. I mean, it'll be proved that they don't exist, and in that case, all these proofs will become very simple because there will be no case of. So the case 1 is there is no exceptional 0. All right. So now, what did I tell you? I told you that we will choose it. We will choose sigma 1. Yeah. So let me choose sigma 1 to be equal to 1 minus C upon log qt to the power some alpha. Okay. Where what is the C? This C is the constant. Does this speak to you? This kind of a result, 1 minus C upon something? This is the zero free region, yeah? C is the constant. In the zero free region. So what is the zero free region? Which we studied this yesterday, that there exists a constant such that beta is less than 1 minus C upon log qt. All right. Now, either chi is non-principal or chi is principal. So suppose chi is non-principal, what happens? Where is my integrand? Okay, it's not on the board anymore, but remember what it was. It was the integral of L prime by L, L prime by L, x bar s by s. Okay, and we are on this contour. So what happens when chi is non-principal? If chi is non-principal, what happens? Who is not feeling sleepy? Yeah? Is this analytic? Yeah. If it is non-principal, it is analytic. There's no problem. Yeah. Problem would be when chi will be chi 0. Yeah. So either chi is principal or chi is not. So begin by chi being non-principal, and then what we have is, then the integrand is analytic. Okay, in C. C is my concept of integration. If not, chi is equal to chi 0 if chi is actually equal to chi 0, what happens? If chi is equal to chi 0, I have L prime by L. What happens? Is there a pole? Yes, S is equal to 1, there is a pole. Yeah. So there is a pole. At S equal to 1. We know this. And the residue is X. Okay. Then what we had minus, which is no longer on the board, but I had an integrand there, minus 1 by 2 pi I, and I'm taking this integral over C, L prime S chi over L S chi, x bar S by S. This is now equal to E0 x x. All right? So the explicit formula now can be written as psi x chi is equal to, I have E0 x, E0 chi, sorry, E0 chi x, and no, let's remove this main term. This is going to be less than x log x square 1 by t plus exponential minus c log x, and that alpha which I took here, okay, by alpha log qt. So Yeah, so this is when I have the case 1, there is no exceptional 0. So the second case now will be when exceptional 0 exists. So this is my case 2. Case 2 is when exceptional 0 exists, exceptional 0 is the Siegel 0. Yeah. So there is an exception. I'm allowed to write an exceptional 0 because I know that if it exists, there is only one. Yeah. I mean, it's already bad enough. We don't want many of them. One is already, there is an exceptional 0, which I call beta 1. And as I told you, there are, what we have to take care is, where is beta 1? Okay. So if beta 1 is greater than or equal to 1 minus c upon something which is not necessarily the same c, some same alpha, but some kind of an alpha 1 log qt. Okay. Now what happens here? What happens here? If beta 1 is greater than or equal to 1 minus some constant times alpha 1 log qt, that means I will get, by suitable choice of sigma 1, I'm going to get a 0, a pole in the contour. All right. So I will choose sigma 1. This time, how would you like to choose sigma 1? The first case, I had chosen sigma 1, 1 minus c log qt by alpha. Okay. So that means 1 minus c, if I take it, I should take now something which is smaller than alpha. Yeah. In fact, even smaller than this alpha 1. So we choose sigma, which is 1 minus, so that the same c, some alpha 2 log qt. Okay. And alpha 2 is less than alpha 1, which is less than alpha. All right. So what will happen now? Can you guess? What's going to happen now inside the contour? Yeah. This, you know the zero free region. Yeah. So beta 1 is greater than 1 minus c. So I get a pole. Now we get a pole where? Inside, but at beta 1. My exceptional 0 is at beta 1. Okay. Now there is a pole inside C, inside my contour, and beta 1. Okay. So this gives what I want, x to the power minus x to the power beta 1 by beta 1. All right. So now put it all together, and this case 2 will be, so psi x chi, my aim, don't forget what we wanted to do. What we wanted to do was to get psi x chi. So this is our case 2 is going on now. So there is this pole. So the explicit formula in this case is psi x chi equal to, so this one will come back, minus x by beta 1 by beta 1, and then another term, big O of x log square x times 1 by t plus this inside your integral x, maybe we can remove this. Mm. 1 by t plus, like before, the exponential of minus c log of x alpha log t. Okay. Do I have the good number of brackets? 2, 3. Okay. So that's okay. So what's case 3 going to be? Who will help me? You have case 1 here, case 2 there. So case 3 is? What remains? What remains? What remains? You're a fan of Pink Floyd? No. What would you study in case 3? So what is not? Case 1 has been done. There is no exceptional 0. Case 2 has been done. There is an exceptional 0 which satisfies this condition. So what should case 3 do? It should be the complement of this. And what is the complement of this? You change the sign. Beta 1, there is still an exceptional 0. This is a subcase of exceptional 0. And the rest of the cases is the complement of this, which is beta 1 this time is, it should be, the complement of this will become less than, yeah? So case 3 will be, there is an exceptional 0. So case 3 is that there is still an exceptional 0. There is an exceptional 0, but the distance is the complement. The exceptional 0, which is beta 1, but this time beta 1 is, the earlier beta 1 was greater than or equal to, so this time beta 1 is less than 1 minus c by alpha 1 log qt. Okay. And this time what is going to happen, so it's this term, yeah, x to the power beta 1 by beta 1. So now x to the power beta 1 by beta 1. So this is what you have to bound. This is going to be less than x exponential minus c log x alpha log t. So what remains to do now is to choose your sigma t, and yeah, and then it's done. Okay, so choose the parameters suitably. Yeah. And then you get this theorem. Okay. So now, of course, there's a proof and all that, but is this a very good theorem according to you? I mean, not that is it a good theorem. Of course, it's a good theorem, but is this result strong? Is this result, what's weak about this result? What's weak about this result is that these are not uniform. You have a dependence on beta 1. Yeah? And if you want to remove the beta 1, if you want to get a result where there is no dependence, want to get a uniform result, this becomes a bad result. Bad result in the sense, a result where the Q, you remember here in this theorem, Q was not so bad, but it really gets worse, and that's what we will show you. Okay, so so the moral of the story is that beta 1, so remark, it's a remark I want to make. It's not because I call it a remark that it becomes a trivial remark. Okay, it's just to distinguish it from a theorem that I call it a remark. So the point we should realize is that the term containing beta 1 yeah, is the main difficulty. Okay, to get any good universal upper bound. Yeah. That it would be good as well as universal. Upper bound. All right. So, yes. It's this one. This is where your when would you have the exceptional zero and when would you not have it? That's the point that is coming from this Q. Okay, you cannot have it for all Q because you might come across this. Okay, so now this is a result for an explicit formula. We have not yet done psi x qa. So that's not very difficult. This is called Page's theorem. I don't know where Page was from. I don't quite know. I think he somehow got overshadowed by Landau. So as a corollary of this theorem, oh, not white. Okay, known as Page's result, I mean proved by him. So psi, now instead of this x chi, I have x with q and a given. This is equal to either x by phi of q plus big O x expo the exp of minus c1 square root of log x if there is no exceptional 0 so if there is no exceptional 0, okay, or it is equal to a term containing exceptional zeros, and this time you're going to still have x by phi q, first main term x by phi q, and then a second, what should be a main term. So this is chi1 a x to the power beta 1 phi q to the beta 1 plus big O x exponential minus c1 square root of log x. Okay. Okay. Here, if beta 1 is the exceptional 0, and chi1, this chi1 is the exceptional character, which gives beta 1. Okay.